My name is Marco Clisson and I'm a researcher at the Italian National Meteorological Institute.
One recent development in the treatment of cancer consists in exploiting the magnetic properties of nanoparticles. In fact, when they are exposed to an electromagnetic field, an alternating field, they develop heat. And the idea is to be able to localize that heat only into cancer cells in order to increase their tendency to die, sparing the healthy cells.
Magnetic nanoparticles can be prepared by a variety of different techniques, including, for example, chemical synthesis. And they come in the form of powders with a more or less spherical shape and a size of the order of a few tenths of nanometers.
When trying to develop this technique to treat cancer, the metrological challenge is to be able to accurately measure the heat that is generated by the nanoparticles when they are submitted to an alternating magnetic field. This task may seem trivial, but it is not possible to measure directly the temperature of the magnetic nanoparticles because of their size. Therefore, it is necessary to disperse them into a medium and measure the temperature of that medium. But the medium will be in thermal contact with the surrounding environment, so all the heat exchanges with the surrounding environment must be taken into account when doing the measurement. In principle, the measurement technique is quite simple. You don't need too many components to set up an experiment for measuring the temperature of the medium in which the particles are dispersed. You need a copper coil that is used to generate the electromagnetic field and, of course, a power supply to drive it. Then you need a holder where you put the particles dispersed in the medium. And then you need a temperature sensor which you can immerse in the medium where the particles are located in order to measure its temperature. The coil is made of copper. A resonant power supply drives the coil at a frequency and with a field intensity that is determined by the number of turns and by the maximum power that the power supply can generate. The sample will be placed in the center of the coil in order to ensure the maximum homogeneity of the magnetic field. The temperature is measured through an optical probe. It is not possible to use any kind of thermometer because its tip will be placed in the same region where there is the electromagnetic field, which will interfere with any thermometer that is made of a metal. So thermocouples or thermistors, etc. will not work. Even semiconductors will not work. Instead, an optical thermometer will do the case, as it implies that no current flows through the thermometer. It is an insulator, and the temperature is probed by optical means through a laser that excites an optical transition of a crystal whose emission frequency will depend on the temperature. In order to prepare the sample, you start with the dry nanoparticles. You take some of them, weight them, and disperse them in a known amount of liquid. For example, 1 milliliter of water. This is an already prepared sample. The medium can be any liquid, in fact, but we chose water because its thermodynamic properties are well known. Once the sample is ready, it can be put into this holder that acts both as a holder as a thermostat. In fact, it contains water that can smooth out the heat exchange between the sample and the external environment. Once everything is ready, we lower the temperature sensor into the Eppendorf tube containing the water-dispersed nanoparticles. In order to perform the experiment, we prepare everything as we described earlier, and then we switch on the magnetic field. When we switch it on, the temperature immediately increases because the nanoparticles convert the electromagnetic energy they receive into temperature that heats the water in which they are dispersed. After a certain time, we switch off the magnetic field. The temperature immediately decreases because the system dissipates heat with the surrounding environment. During a typical magnetic hyperthermia experiment,
we collect the temperature of the water as a function of temperature for 1 hour during heating and for another hour during cooling. A typical magnetic hyperthermia experiment consists of 2 measurements. One is the measurement that we discussed in the previous minutes, the red curve of the magnetic nanoparticles dispersed in water. But a second measurement must be done with just the water without the magnetic nanoparticles, the blue curve, because as you can see, there is a spontaneous heating also of the water without the nanoparticles. This is due to the ionic currents flowing in the water, but also to the thermal exchange between the water and the exciting coil, which of course it's up a little bit during the application of the electromagnetic field. In order to be able to extract the heating power of the nanoparticles, it is necessary to have an accurate model of the thermal exchanges between the different components of the system, namely the particles, the water in which they are dispersed, and the surrounding environment, through a suitable set of differential equations. By fitting the experimental data and through a suitable calibration of the setup that involves an accurate modeling of the blue curve here, just the water, it is possible in the end to fit the data with the green curve here and extract a parameter that is called the specific loss power that gives you the heating capability of the particles. The specific loss power is the power, the watts released by the particles per unit mass. The specific loss power is an intrinsic parameter of the magnetic nanoparticles. Measuring it allows to compare different materials to establish which one has the best performance and in which conditions. However, in order to be able to really apply the nanoparticles into clinical applications, it is necessary to study also the interaction between the nanoparticles and the surrounding environment, that is, the medium in which they are dispersed. Because the heat exchange between the particles and the medium will be very, very different depending on the medium. And so the temperature that the cancer cells will reach during the application of magnetic hyperthermia will depend not only on the magnetic nanoparticles, but the dose will depend on the amount of particles, but also on the kind of tissue and the way the heat is transported in the